last lecture, we were discussing the square well potential problem. This is a one-dimensional problem where we were discussing stationary states, basically the energy eigenstates. Let me quickly recapitulate some of the steps that we worked out in the last lecture so that we can continue from there and discuss the square well problem in greater detail in this lecture. So we had the square well potential. This was V of x versus x, and then in the negative region you had this square well. So out there and out here at minus a and plus a, the well began. The potential itself was minus V naught, where V naught is a positive quantity. This was in region 2, which is inside the well. Then there were regions 1 and 3 outside the well, and the square well potential was given by 0 for mod x greater than a and was equal to minus V naught for mod x less than a. Now in this case, we wrote out the wave functions in the 3 regions, and basically because the wave function has to vanish at spatial infinity, we had psi 1 of x that was in region 1 that was simply a e to the alpha x. We were considering bound states, and therefore it's important to note that the energy was less than 0. The whole idea was to see if classically forbidden regions are accessible in quantum physics. So this came because alpha squared was a positive quantity, which was given by minus 2m e by h cross squared, and we also said that alpha was greater than 0. Since e is negative, minus 2m e by h cross squared is positive. So this is for an energy which is less than 0, somewhere out there. Psi 3 of x was b e to the minus alpha x. This was put down so that the wave function vanished at x equals plus infinity. And we had psi 2 of x, which was c cos beta x plus d sine beta x, where beta squared was 2m by h cross squared e plus V naught. And since e is less than V naught plus e is a positive quantity, and therefore beta squared is positive with beta greater than 0. That was our definition. Now given this, we matched the wave functions and the derivatives at x is plus a and x is minus a, and then we found that we could write the following equations: a plus b e to the minus alpha a was 2c cos beta a. Let me refer to that as equation 1. A minus b e to the minus alpha a was minus 2d sine beta a. And then of course the derivatives, when you differentiated it, it pulled down an alpha or a beta depending on the situation, and you had alpha times a plus b e to the minus alpha a was 2c beta sine beta a, and alpha times a minus b e to the minus alpha a was 2d beta cos beta a. So these were the 4 equations that we had written down, and finally we discussed 2 possible solutions to this problem, depending on whether a was not equal to b. If a is not equal to b, then a minus b is not 0, and therefore I could divide 4 by 2 and that gave me one solution for alpha. If A is not equal to minus B, this does not disappear, and I could divide equation 3 by equation 1. That gave me another solution for alpha. So we had solution 1 and 2, so let me just write that down. Solution 1 came by dividing equation 4 by equation 2. So it automatically assumed that A was not equal to B, and therefore I could do this, and that told me that alpha was beta. This was equation 4 divided by 2, so it gave me a minus beta cot beta A. That was solution 1. Then we had solution 2, and that assumed that I would be able to divide 3 by 1, equation 3 by equation 1, which means A is not equal to minus B. The solution itself came by dividing equation 3 by equation 1. When you do that, you get alpha is equal to beta tan beta A. So this was the second solution. So these are possible solutions, and then we use this to also find out the allowed values of beta A for the different cases, because if alpha is greater than 0 and beta is greater than 0, beta A is restricted to certain values. So let's look at just what we had in the last lecture. So if I plotted beta A, there were only some allowed regions. Let me look at solution 2. Solution 2 says that alpha is equal to beta tan beta A. A very crucial input was this, that we had a parameter delta, which was h cross squared by 2m A squared, and that led us to an equation alpha squared plus beta squared times A squared in terms of V naught by delta. So once you substitute for alpha squared and beta squared from there, you find that there is an expression for V naught by delta which tells you what is the value of V naught in terms of the strength of the potential, and we realized that all we had to do was plot mod cos beta A versus beta A, and therefore we could choose various values for V naught by delta. That gave me the slope of the equation delta by V naught to the power of half beta A, and because alpha was equal to beta tan beta A and alpha and beta are both positive, beta A was allowed to have values only from 0 to pi by 2, pi to 3 pi by 2, and so on. There were certain regions where you could have admissible solutions, and since this was a plot of modulus of cos beta A versus beta A, we found that this was the cos function. The crucial point is there is one point of intersection in this, and therefore there was one possible value of beta between 0 and pi by 2. Let me call that beta naught, that lies between 0 and pi by 2. Maybe it's better to write beta A between 0 and pi by 2. But then you see the next solution happens between pi and 3 pi by 2. There is a cut there. That's an allowed solution, and that comes from alpha is equal to beta tan beta A. That is solution 2. As I said in my last lecture, you could have looked at solution 1, and if you had done that, alpha is equal to minus beta cot beta A. That was solution 1. And this time the allowed values of beta A, because alpha is greater than 0 and beta is greater than 0, the allowed values of beta A are between pi by 2 and pi, 3 pi by 2 to 2 pi, and so on. In this case, you end up plotting the function modulus of sine beta A. I fix a V naught by delta, that would give me the slope. And if it's modulus of sine beta A that needs to be plotted, I have the sine function and notice that there is one solution out here for beta A between pi by 2 and pi. This is very crucial. So, since that solution happens between pi by 2 to pi, let me call that beta 1 for beta A between pi by 2 and pi. So, if you compare beta naught, the first solution corresponds to beta A lying between 0 and pi by 2. Beta 1 comes from the other solution, alpha is minus beta cot beta A, and that is for beta A lying between pi by 2 and pi. Then beta 2, the next solution, is here. This corresponds to beta A between pi and 3 pi by 2. And then look at the solution between 3 pi by 2 and 2 pi. That comes from here, because the allowed value of beta A in this case is pi by 2 to pi and 3 pi by 2 to 2 pi. Might be useful to have a colored chalk, that and this. And I have a solution here. So, I will call that beta 3 between 3 pi by 2 and 2 pi, and so on. So, you get a set of discrete values for beta. We can call them beta sub n. N is equal to 0, 2, 4, etc. came from alpha is equal to beta tan beta A. N is equal to 1, 3, 5, and so on came from alpha is equal to minus beta cot beta A. Now, once I have beta sub n, I know that the energy is quantized, because look at this here. I have beta sub n squared is 2m by h cross squared E n plus V naught, and therefore, h cross squared by 2m beta n squared minus V naught is equal to E n. So, I can find out the corresponding values of the energy. The important thing, which I also emphasized last time, was that however shallow the well may be, however small the strength of the potential may be, you find that there is definitely one solution, and that solution comes for beta between 0 and pi by 2. There is always a solution. That is an important feature of the quantum system. If you look at this, and from here, if we try to find out what is E n, there is a nicer way of doing this problem. Please recall that delta was h cross squared by 2m a squared. And therefore, I can write h cross squared by 2m as in terms of delta, and I can write that as delta a squared. So, therefore, this implies that delta a squared beta n squared minus V naught is equal to E n. In other words, I can pull out the V naught, and I just have delta by V naught beta n a the whole squared minus 1 is E n. What is nice about writing it in this fashion is that what I have put down inside the square braces, delta by V naught times beta n A the whole squared, this can be read off from here. And therefore, this is a more instructive way of writing it. The quantity within the square braces can be read off directly from the plot, and therefore, I get various values of En once I know V naught. V naught is something that I have decided on to begin with, decided on the strength of the potential. In other words, I know V naught by delta. So, this is what we have in terms of eigenvalues, the energy eigenvalues. Let us look at the energy eigenfunctions. Now, as far as the energy eigenfunctions are concerned, we will take up solution 2 first. Recall that solution 2 gave us beta naught, beta 2, beta 4, and so on. This is all for E less than 0. We are looking at bound states, and alpha was beta tan beta A. This was solution 2. In order to get alpha is equal to beta tan beta A, I had divided equation 3 here by equation 1. So, now I would like to take this value of alpha and substitute it in equation 4. So, from equation 4, beta tan beta A times A minus B e to the minus alpha A is 2d beta cos beta A. So, I have already used equation 4. Now, I am left with equation 1, and I would like to substitute equation 2, and I would like to substitute for A minus B e to the minus alpha A from equation 2, and therefore, I have minus 2d beta sine squared beta A is equal to 2d beta. From the tan, I can take the cos there, and that gives me a cos squared beta A. So, this cannot happen because it tells me that sine squared beta A is minus cos squared beta A. Not possible. This implies that d is equal to 0. So, going back to these equations, if d is equal to 0 from equation 2, I know that A is equal to B. Started off by saying that A was not equal to minus B, that is okay. We have just now seen that A is equal to B plus B. So, if A is equal to B and D is equal to 0, I can find A in terms of C. So, that tells me that 2A e to the minus alpha A from equation 1 is 2C cos beta A, and therefore, A itself, which is also equal to B, is C cos beta A e to the alpha A. So, now I can write out the wave function in the different regions. So, let us see, psi 1 of x is A e to the alpha x. So, we are looking at solution 2. Alpha is beta tan beta A. It gave me A equals B, and that can be written in terms of C as C cos beta A e to the alpha A. D was equal to 0, means that psi 1 of x, which was A e to the alpha x, can be written as C cos beta A e to the alpha A e to the alpha x. Boundary condition is satisfied because when x goes to minus infinity, the wave function goes to 0. Psi 2 of x, the term with D as a coefficient dropped out. So, you just have C cos beta x. Psi 3 of x, A was equal to B, and therefore you had C cos beta A e to the alpha A e to the minus alpha x. The minus here was selected, was chosen by us so that when x goes to plus infinity, the wave function vanished. There is another check. When x is equal to minus a, psi 1 of x matches with psi 2 of x, which is the way it should be. And when x is equal to plus a, psi 2 of x matches with psi 3 of x. We can also check that the derivatives match. There is a very interesting feature that comes out here. This wave function, the total wave function, has three parts: psi 1 in the region x less than minus a, psi 2 in the region minus a to plus a for x, and psi 3 plus a to infinity. Now we find that this wave function is a symmetric function of x, because we should really be writing cos beta n out here. But these solutions correspond to n equals 0, 2, 4, and so on, because we got it from alpha is equal to beta tan beta a. This wave function is a symmetric wave function, because when x goes to minus x, psi 1 goes to psi 3 and psi 2 is left invariant. So what we have seen is that under the parity transformation, that is when x goes to minus x, the wave functions corresponding to the eigenvalues beta naught, beta 2, beta 4, etc. In other words, energy eigenvalues E naught, E2, E4, etc. have even parity. They are symmetric about x is equal to 0. This means that if I plotted, for instance, the ground state wave function, the wave function would look something like this. That's x is equal to plus a, that's x is equal to minus a. Notice that it's a cos function here, but then it doesn't taper off there, goes all the way here. There's an exponential fall off. So there is a certain penetration or a leakage into the classically forbidden regions. This is psi 0 of x, for instance. There is a penetration into the classically forbidden regions. In other words, there is a non-zero probability of seeing the particle with mass m outside the square well potential, although its energy is less than 0. But then that's an exponential fall off, which comes out from this term e to the alpha x here and e to the minus alpha x there. So certainly two important features of quantum physics emerge. One, in a bound state, the energy levels are discretized. Two, although the energy is less than 0, quite in contrast to classical physics, I can see a non-zero probability of leakage into the classically forbidden regions of the wave function. So this is as far as solution 2 is concerned. So let us look at solution 1. Solution 1, again E is less than 0, and we repeat our argument. Now for solution 1, that was alpha is equal to minus beta cot beta a, and remember the values that beta could take were beta n with n equals 1, 3, 5, and so on. I got the equation alpha is equal to minus beta cot beta a by dividing equation 4 by 2. So I can well substitute for alpha now in equation 3. So if I did that, minus beta cot beta a, so from equation 3, minus beta cot beta a plus b e to the minus alpha a, is 2c beta sine beta a. So I have used equations 4, 3, and 2, but I am left with equation 1, from which I will substitute for a plus b e to the minus alpha a. Therefore, from equation 1, minus 2c beta cos beta a, so that gives me a cos squared beta a, is 2c beta. I can take the sign from here there, sin squared beta a, and that is not possible because that tells me, as in the earlier case, this time again cos squared beta a is equal to minus sin squared beta a. Therefore, this implies that c is 0. So, going back to these equations, if c is 0, it means that a is minus b. Recall that we got this solution by saying a is not equal to plus b, and what we have seen is that a is minus b. So, if a is equal to minus b and c is 0, I can substitute here, and I have minus 2b e to the minus alpha a is minus 2d sin beta a. So, I can solve for b in terms of d. And this implies that b is equal to d sin beta a e to the alpha a. So, a is minus d sin beta a e to the alpha a. So, I have got the solution corresponding to the various wave functions now. So, psi 1 of x, psi 2 of x and psi 3 of x can be written for this case. So, let me do that here. So, this is solution 1. Alpha is equal to minus beta cot beta a. This tells me that a is minus b, and that quantity is minus d sin beta a e to the alpha a. Also tells me that c is 0, and therefore, I can write the various wave functions now. Psi 1 of x is a e to the alpha x. So, it is minus d sin beta a e to the alpha a e to the alpha x. Psi 2 of x, since c is 0, it is just d sin beta x. And psi 3 of x is b e to the minus alpha x. So, I can write that down as d sin beta a e to the alpha a e to the minus alpha x. This corresponds, of course, to quantized values of beta, beta 1, beta 3, beta 5 and so on. And you can see that this wave function also has a definite parity, because if you take x to minus x, psi 1 of x goes to minus psi 3 of x, and psi 2 of x again is an odd function of x. So, these states have odd parity, they are odd parity states. So, what we have come across now is that the ground state has even parity, the first excited state has odd parity, the second excited state has even parity, and so on alternately. The point is this: we saw the same thing in the case of the linear harmonic oscillator, where the states came with definite parity, the energy eigenstates, once more alternating between even and odd parity, the ground state having even parity. In that context, I had explained that this feature arose because the Hamiltonian commuted with the parity operator. It is the same reason that I would give here, because the square well itself, if you look at the potential form, the form of the potential was a symmetric function of x, went from minus a to plus a, and it was symmetric about the origin. And therefore, the Hamiltonian was a symmetric function of x, as a result of which it commuted with the parity operator, and hence you could find a complete set of common eigenstates of the Hamiltonian and the parity operator. Now, these are energy eigenstates, eigenstates of the Hamiltonian. Therefore, they should be eigenstates of the parity operator. This is indeed the complete set of common eigenstates between H, the Hamiltonian, and P, the parity operator. And since they are eigenstates of the parity operator, and the only eigenvalues allowed are plus or minus 1, they are states with definite parity, either symmetric under x going to minus x or antisymmetric under x going to minus x. So that is what we have seen in this problem. So much for the bound state solution. They are energy eigenstates with definite parity. Even for energy less than 0, there is a possibility of leakage into the classically forbidden regions, and also the energy states are discretized. So this is a good place to look at what happens if you increase E and if the energy were positive. So let us look at the same problem, but now the energy takes positive values. So we have the square well potential. This is V of x versus x, and this is x is plus a and that is x is minus a. This is minus V naught, where V naught is positive, except that now we look at energies greater than 0. This is the reference level, this is the origin. So the energy is greater than 0, and you have regions 1, 2, and 3. Even from a very classical viewpoint, it is clear that the particle with mass m can move all over. It is not as if regions 1 and 3 are forbidden. So this whole region, region 1, similarly region 3, are accessible regions to the particle, simply because it has enough energy to go across. So this is not a situation where we would be taken by surprise if quantum mechanically also the particle behaves like as if it is free, because there is enough energy to overcome the potential. In other words, it will not be surprising if the solutions that we have for the energy eigenstates are plane wave solutions, because it is as if the particle is a free particle. Although there is a potential, there is enough energy to overcome the potential in region 2, and of course in regions 1 and 3 it is genuinely free. So let us look at the wave functions in the 3 regions. If you look at region 1, the Schrödinger equation there is no V, but there is an E, and the energy is positive. Since the energy is greater than 0, I define an object 2m E by h cross squared as some positive value k squared. So it is greater than 0, and therefore the solution would be psi is a1 e to the I k x plus a2 e to the minus I k x in region 1. So I have plane wave solutions in region 1. The same equation holds in region 3, and therefore I have the following solutions in region 1, 2, and 3. So region 3 again the same type of solutions. Now look at region 2. In region 2 we have said that the energy is greater than 0. The equation itself in region 2 would have been minus h cross squared by 2m d2 psi by dx squared plus v psi is E psi. So therefore, I had an E minus V psi out here. But V was minus V naught, and I have this quantity E plus V naught psi. But this is all right, because then d2 psi by dx squared is minus 2m by h cross squared E plus V naught psi. And 2m by h cross squared E plus V naught is a positive quantity. So I define beta squared as 2m by h cross squared E plus V naught as before. And therefore, in region 2, I have my old solution C cos beta x plus D sin beta x. Now, in order to make a comparison, it would be useful to write this also as exponential of I beta x and exponential of minus I beta x. So I can write it as C1 e to the I beta x plus C2 e to the minus I beta x. They are the old familiar solutions that we had earlier, except that I'd like to write it all in a plane wave form to show that essentially it behaves like as if it's a free particle. But then if you look at these equations, if I matched the wave functions and derivatives at x is equal to plus a and x is equal to minus a, I'll get two conditions out here at x is equal to minus a, and here at x equals plus a. If I matched psi 2 and psi 3, I'll get two more conditions. So I have 4 conditions, but I have 6 unknowns, and therefore it would not be possible to determine the coefficients in this case, the coefficients being k and beta. In other words, there is no particular relationship between k and beta. In the earlier example, there was a relation that said that alpha was either beta tan beta a or minus beta cot beta a. Such a thing is not possible in this case, because I do not have a sufficient number of equations to solve for so many unknowns. And since there is no such equation relating k to beta, it's clear that there is no control on the situation. In other words, since k and beta are functions of E, it's obvious that any value of E is allowed. There is nothing that constrains the value of E and makes it discrete or even says these are the only possible values of E. So all values of E are allowed. All values of E greater than 0 are fine. The energy is therefore not discretized, which means that you get a continuum of states. The word continuum is used in contrast to the word discrete. So instead of a discrete set of energy eigenstates, I have a continuous set of energy eigenstates. So that is what happens in this problem. Not very surprising. It's the kind of thing I would expect even in classical physics. Not as stunning a result as there is a classically forbidden region and there is leakage. On the other hand, instead of looking at this problem in detail, it's worth looking at another problem which also deals with plane waves, and that is the problem of a potential barrier. Because in classical physics, if the energy is not enough to cross a barrier, then there is nothing like tunneling across the barrier. In quantum physics, there will not only be tunneling across a barrier, there will also be leakage across the barrier. Therefore, I will discuss the barrier problem now to show the possibility of tunneling and the possibility of reflection from the barrier. So let us look at the problem of the potential barrier, which is a kind of complementary problem to the well. So for the potential barrier, I have a one-dimensional potential barrier, and that's like this, where this is positive and this is x is equal to minus a, and that is x equals plus a. So it is 0 outside the barrier. So I have regions 1, 2 and 3. So to show you the barrier, that is 0 there and 0 here, 0 all the way, and this is a square potential barrier. It is to be seen as a square potential barrier. Okay, so that is where we are. Now if I write out the equations, the problem is the following. I imagine that there is a wave with momentum h cross k which is incident on this barrier from the left. A part of it can be reflected. I should first of all put in that possibility and see if it is consistent with what I have, and the rest of it could be transmitted. The point is, in region 3, how much of what went through actually tunneled across? That is the question that we ask. So let me write out the Schrodinger equation in the various regions. In region 1, minus h cross squared by 2m d2 psi by dx squared is equal to E psi. The point is this: we give a certain amount of energy which is greater than 0, but the height of the barrier is more than the energy that we give. So V naught is greater than E, and both of them are positive quantities. Therefore, I have d2 psi by dx squared is minus 2m E by h cross squared psi in region 1. 2m E by h cross squared is a positive quantity because E is greater than 0. I call that k squared. Therefore, the solution for psi in region 1 is clearly going to be a1 e to the I kx plus a2 e to the minus I kx. So e to the I kx represents a wave with momentum h cross k hitting this barrier from the left. E to the minus I kx has a coefficient a2 which should give me the probability amplitude for reflection from the barrier, because that would correspond to a wave with momentum minus h cross k. So this is in the region psi 1. Of course, in the region psi 3, I will have an analogous equation. Here, so I will have psi 3 is b1 e to the I kx. Normally, I should also write plus b2 e to the minus I kx. I am not, because I am not allowing for reflection out here. There is a wave that just tunnels across, if at all it is possible, it tunnels across. There is nothing like a reflection into the barrier. And therefore, in the region 3, the problem that I envisage can only have a solution b1 e to the I kx corresponding to a wave traveling this way with momentum h cross k, traveling along the positive x axis. So the problem posed is this: there is a wave with momentum plus h cross k. In region 1, hits the barrier from this side, part of it gets reflected. The question is how much of it can tunnel across into region 3. Can you have a non-zero value for b1? Now as far as region 2 is concerned, we can always write out the equations for region 2. In region 2, this is the barrier problem, but we should remember that b naught is greater than E and E itself is greater than 0. You have minus h cross squared by 2m d2 psi by dx squared plus V psi is equal to E psi, and therefore d2 psi by dx squared is minus 2m by h cross squared E minus V naught psi, which is 2m by h cross squared V naught minus E psi. And this quantity is positive because V naught is greater than E. So I define 2m by h cross squared V naught minus E as a positive quantity. We've used alpha and beta, so now let me use gamma, gamma squared. So my equation is this: d2 psi by dx squared so I have minus gamma squared psi equals 0. The solution psi 2 of x is clearly going to be, I have used a1, a2, b1, b2. So, let me say c1 e to the gamma x plus c2 e to the minus gamma x. So, this is my solution. So, in a sense the solutions are just the opposite of what we had in the case of the square well potential, where you had c e to the ikx plus d e to the minus ikx within the square well, and outside you had exponentially falling things, whereas here it is the other way around, and these are my solutions. So, let me just write that down clearly. In region 1, so this is the barrier problem, one dimensional potential barrier. V naught is greater than E, which is greater than 0. 2m E by h cross squared is k squared, and 2m V naught minus E by h cross squared is gamma squared. And psi 1 was a1, psi 1 is of course a function of x, and that is a1 e to the ikx plus a2 e to the minus ikx. Psi 2 of x is c1 e to the gamma x plus c2 e to the minus gamma x, and psi 3 of x, given the kind of problem that we are envisaging, is simply b1 e to the ikx. I want to emphasize the following. It is not as if we are considering a wave traveling in time. We are not looking at any dynamics in this problem. Should not imagine that there is a time period over which the wave travels and start wondering why is it that time does not figure in this equation. We are merely considering a wave of this form. So, clearly the reflection probability amplitude for reflection would be a2 by a1 at this boundary, x is equal to minus a, and therefore reflection probability is modulus of a2 by a1 the whole squared. Similarly, we can write the transmission probability the amplitude for transmission or tunneling, quantum tunneling, depends on what b1 is given a1. So, the amplitude for tunneling is b1 by a1, and therefore the probability for tunneling is modulus of b1 by a1 the whole squared. Question is, how do you solve for these? There is a very systematic way of doing this. First of all, match the wave function and derivatives at x equals plus a, and that should give me the ratio c2 by c1. That is the first step. So, there are a series of steps involved, which is just a lot of algebra. So, I would request you to work out these steps, and I will put down the results for you so that you can see them and try to get each of them. I will explain to you how exactly these results are got, and then I will discuss the result with you in brief. So, treat this as a set of exercises. First of all, match the wave function and derivatives at x equals plus a. Well, that would be like matching psi 2 with psi 3. So, that will involve B1, C1 and C2. Since the derivative would involve B1 and the wave function also involves B1, you can divide the derivative equation, the derivative matching equation with the wave function matching equation, eliminate B1 and get the ratio C2 by C1. Now, once that is done, you match the wave function and derivatives at the other boundary, x equals minus a. Now, that will involve C2, C1, A2 and A1. Feed in the value of C2 by C1 from here and get this expression for A2 by A1. Our aim is to find the transmission probability and the reflection probability. So, the aim is to find B1 by A1. Remember that B1 is the coefficient of the wave that tunneled across to region 3 and A1 was the incoming wave e to the ikx, A1 e to the ikx was the incoming wave, and therefore, if you want to find B1 by A1, you match the wave functions again at x equals plus minus a using these as inputs, C2 by C1 and A2 by A1. That would give you this expression for B1 by A1, this expression here, the mod square B1 by A1 mod square will give you the transmission probability, which I have called T. So, this is the probability of tunneling, if you wish, tunneling probability. That quantity can be written in this form. You write everything in terms of V naught and V naught minus E, because once more it is a question of what is the deficit energy V naught minus E and how well can the tunneling happen depending upon V naught minus E. Look at this expression. I wish to comment on this expression before I conclude. This is sine hyperbolic squared of an object twice root of V naught minus E by delta, where delta itself is h cross squared by 2 m a squared. That was the reference in terms of which we could define the strength of the potential. Now, this quantity can be written in terms of sine hyperbolic, this argument can be written in terms of e to the y and e to the minus y. Now, as long as the argument y is not far less than 1, this can be well approximated by the exponential, and therefore, the square gives me e to the minus 4 root of V naught minus E by delta. So, I will use e to the y and not e to the minus y. So, that gives me e to the 2y, where y is this argument, but there is an inverse here, and therefore, it becomes e to the minus 2y, which was e to the minus 4 root of V naught minus E by delta. So, this is revealing because it tells me that V naught minus E, remember that V naught is greater than E, which is greater than 0. So, depending upon the energy V naught minus E, there is going to be an exponential fall off of the tunneling. So, this quantity has to be scaled by delta because it tells me what the deficit energy is in terms of delta, and there is an exponential fall depending on that. However, there is a tunneling, there is a non-zero tunneling probability, which is quite unlike, not just quite unlike, in stark contrast to what you would expect in classical physics, where you have an energy in this situation which is less than the potential V naught. So, the crucial point is this: for an energy which is less than the potential barrier, you do not expect in classical physics the object to tunnel across to region 3 if it came from region 1. In quantum physics, on the other hand, there is tunneling. To summarize, therefore, both in the problem of the square well potential and in the problem of the potential barrier, these are complementary problems, we realized that there were certain very stunning aspects of quantum physics. Leakage into classically forbidden regions, of course discretized energy values, for the square well potential when the energy was less than 0, and a non-zero tunneling probability as also a non-zero reflection probability. Because you will notice that A2 by A1, the probability amplitude for reflection, is not 0. This is the expression for A2 by A1. There is a non-zero reflection probability, there is a non-zero tunneling probability, and you will be able to show that the probability of reflection, which is modulus of A2 by A1 the whole squared, is 1 minus the probability of tunneling probability. Naturally, because you are not allowing for stickiness in the barrier or anything like that, absorption in the barrier, therefore it either reflects or it tunnels, the total probability being 1, the reflection probability plus the tunneling probability must be equal to 1. So these are the startling features that emerge in quantum physics, quite in contrast to a classical problem of the same kind.